Dear fellow astrobiologists, I warmly greet you to my presentation, Extremophiles, the first Martians ever. My presentation is based on a scientific paper which did a study on two bacteria strands and the possible survival on Martian-like conditions. The contents of my presentation. First, I will give you a brief introduction on the topic and the scientific paper. Then I will talk about the materials and methods they used during the studies, what results they got and their discussion, a brief discussion on them, and last but not least, a conclusion on the whole topic. But first I would like to start with a quote from Buzz Aldrin. He was a member of the Apollo 11 mission. He was the second man to walk on the moon. Just as Mars, a desert planet, gives us insight into global climate change on Earth, the promise awaits for bringing back to life portions of the red planet through the application of Earth science to its similar chemistry, possibly reawakening its life-bearing potential. So yeah, people already had hope that Mars could be inhabited by organisms. This quote got me really excited, and I hope you're as excited as I am for the following informations. Introduction. First, I will talk about extremophiles, then analog sites. After that, I will tell you something about the Botioxella sp and the Salinisphaera shabanensis bacteria strands. And then I will talk about the conditions on Mars and what the goal of the study was. Extremophiles. What are extremophiles? Extremophiles are organisms which are able to thrive in natural extreme environments. On Earth, there are many natural extreme environments. They are extreme because some physical constants are very extreme there. For example, the temperature can be very high or very low, the pH value, the salinity, the hydrostatic pressure, or the availability of water, oxygen, and other valuable nutrients which are necessary for survival. There are extreme sites and analog sites. Analog sites are extreme sites which resemble environments in space or in other planets. In this case, we're looking at analog sites which resemble the conditions on Mars. The first analog site is the Islinger Mühlbach in the Sippenauer Moor, which is located in South Germany. It's a picture of the Islinger Mühlbach. It looks like a forest, but in actuality it's a lake. Yeah. It has low organic contents, temperature is very low there, the environment is an ocean. There are sulfur compounds which possibly are possible energy storage compounds, and it's the home of the Butioxella sp, one of the strands. I will go into further details later. Another analog site is the Shaban Deep, which is located in the northern Red Sea. Its characteristics are the high salinity, the anoxian environment, at the varying levels of hydrothermal input, the high hydrostatic pressure, the sharp brine seawater interfaces which can greatly vary in, for example, amounts of particles, and the Shaban Deep is the home of the Salinisphaera shabanensis. The Butioxella sp. The Butioxella sp belongs to the Enterobacteriaceae family. It's a gram-negative bacteria. It's facultative anaerobic, motile, The appearance is rod shape, rod likely, just like in the picture. Now something brief on the Solnisphera shabanensis. It belongs to the gamma proteobacteria. It's gram-negative also facultative anaerobic, which is a must if you want to survive in space. Or on Mars where oxygen is sparse. It's monotrichosis. It's very versatile and resilient. Conditions on Mars. What kind of conditions would those bacteria would have to withstand on Mars? On Mars, the availability of water and nutrients is very low. The salinity is very high. Mars has a thin CO2 dominated atmosphere with not much oxygen there, which means there's no ozone layer, which does not absorb any UV radiation, so there is a high UV radiation influx on the surface, as well as a low ionizing radiation influx on the surface. The surface is specialized with the morphoglyph. It's like this dust-like accumulation of minerals, which is like thin grains, sand grains, which is all over the surface of Mars. What was the goal of the study they did? So in 2025, the Maxim space mission will hopefully launch, and they're in search of suitable candidates. They're going to study organisms on the ISS, on the Columbus module, if they're able to survive in Martian-like conditions. One goal is if they want to see if Butaxial sp and Solnisphera shabensis will survive Martian conditions. They want to collect data and therefore prepare themselves for the Maxim mission, while as well gaining some insights on the behavior of organisms in Martian conditions. Yeah, so now that we got everything we need, our bacteria are armed and ready, and let's see if they will survive this study. The materials and methods they used in the study. First, I will talk about how they cultivated the strand, which substances they added, how they observed the strands microscopically, how they desiccated the cells, what kind of irradiation treatment they did, how they evaluated the survival fraction. So cultivating the strands. So for Buteo they used a triptych soy broth, for short TSP, and the triptych soy agar plates. The Buteo SP reaches its stationary growth phase in 24 hours, while the Solnisphera japanensis reaches its stationary growth phase in 24 to 48 hours. Solnisphera was also cultivated in a marine broth and on marine agar plates. The whole experiments were done in anaerobic chambers, like the one depicted on the left of me. What kind of substances did they add to help the bacteria strand survive? They added sugars, mainly sucralose and trehalose, depicted over here. Then low molecular substances, ectoine and betaine. And they added Mars regolith simulants. And these Mars regolith simulants, you can buy this on the internet. It's just like it simulates the dust-like regolith on Mars on the surface. Yeah, there are many kinds of Mars regolith simulants. This MGS-1S is like the original one. The MGS-1S is a bit more sulfuric heavy, and the MGS-1C isn't very important at the end. How did they observe the bacteria and changes in the samples? For the bacterial cells, they used the API staining. It's like a fluorescent staining, which allows them to later see them under the microscope. And for the simulant, for the regolith, they used scanning electron microscopy, so they could have a nice picture of the structure and the surface of these particles. Desiccation of the cells. Desiccation basically means drying, because the bacteria would be diluted in some kind of dilution. Is PBS mainly, and yeah, and the soy broth and the marine broth. Before desiccating the cells, they obviously determine the growth and the concentration. Then they tried and counted the numbers of cells. They did this for a whopping 140 days. They diluted them in phosphate buffered saline (PBS), but they used two kinds of PBS. The main difference between the PBS is the one for the Excelia and for the Chabanensis, they had the PBS was much more concentrated in natrium chloride. They also had control colonies, so they were able to see the differences with non-altered or non-tasted colonies. They always wrote down the number of grown colonies. They used these TOMA sets for counting the grown colonies. What kind of irradiation experiments did they do? They did three kinds. The first one was the polychromatic UV in liquid. They didn't dry the cells. There they measured the absorbed light in the spectrum of 200 to 400 nanometers, which is like the spectrum which causes damage to our organismic cells. For the measurement, they used a Hitachi spectrophotometer. Then they did a monochromatic UVC and ionizing radiation experiment. There they measured the absorbed X-rays at the wavelength of 254 nanometers using a unidose dosimeter. And lastly, but not least, they did a polychromatic UV irradiation experiments in the dried cells. There they measured the absorbed light in the spectrum of 200 to 400 nanometers using a Trex box. These were the measured absorptions. Only the TSP, the broth for the potentiella. Then here they diluted the bacteria 1 to 10. Then they added the MGS-1S and PBS. And this is for Chabanensis. The marine broth 1 to 10 dilution, adding MGS-1S and PBS. You can see that diluting and adding the MGS-1S protected the bacteria from these harming UV radiation, and therefore they absorbed way less of these harmful radiations, UV radiations. Then the evaluation of the survival fraction. They did these experiments 3 times. Then they had, for the survival fraction, they had N and N0. N was the desiccated and or irradiated samples, and N0 was the non-desiccated, non-irradiated liquid control colonies. Dividing N with N0, you will get the survival fraction. And using a sigma plot, with the help of linear regression, they were also able to calculate F10 and D10 values. The F10 value describes the fluence required to reduce the survival by 1 magnitude. The D10 value described the dose required to reduce the survival by 1 magnitude. These belong to the irradiation experiments that they did. So let's see what kind of results they got. First, I will talk about effects of added substances on desiccation tolerance of the mixed cultures, survival after polychromatic UV in liquid and after desiccation, survival after exposure to UVC to 154 nanometers and ionizing radiation in liquid, and microscopic observations which were made. Let's see if our little warriors survived the study. What kind of effects did the added substances have on desiccation tolerance? On the standard conditions, no growth was visible after 98 days of desiccation. However, if you had MgS1S at a weight volume of 0.5% and sucrose at a concentration of 0.1 molar, both strains survived at least 140 days. When I say at least 140 days, they only did the study for 140 days. After that, they canceled the study because the maximum mission only lasts 3 months, so any further data was not necessary. Here you can see in the graph these lower graphs are the standard conditions, but these graphs up here are the bacteria with the MgS1S and sucrose, and there you can see the survival is way higher if you had the MgS1S and the sucrose than the standard conditions. This was quite shocking to me. I wouldn't have thought that like this regolith would have such a huge impact on the survival of these bacteria. The survival rate of Butioxella only decreased by 1 magnitude in the span of 140 days, while the survival rate of Schabanensis only decreased by 2 magnitudes over 140 in the span of 140 days. Desiccation tolerance of the mixed cultures. Here they looked at how if the two bacteria strands would undergo symbiosis and if there would be any benefit for them to work together or not. Concerning the storage, there was slight influence in the absolute amount of cells. If you look at them separately or mixed, there's a slight influence over here. However, the survival of desiccation was slightly better when the two bacteria strands were mixed together than separately, which possibly indicates that they do undergo some symbiosis. However, how relevant this slightly improvement of survival is a bit hard to tell. Maybe if they would have prolonged the duration of the experiment, maybe there would have been a stronger difference, but it's only speculation. But yeah, mixing the two cultures together, there was a slight increase on survival of cell desiccation. Now the irradiation experiments they did. These two graphs show the two bacteria in liquid form, and these two in the desiccated after desiccation. But here you can also see adding MGS1S always increased the survival fraction by a huge margin, which is again a strong input that MGS is crucial for microorganisms to survive on Mars. Yeah. Now the UVC 254 and ionizing radiation in liquid with the F10 and D10 values, which I already described. F10 describes the fluence required to reduce the survival by 1 magnitude. Over here, I'm sorry. And the D10 those required to reduce the survival by 1 magnitude over here. Yeah. What kind of microscopic observation were they able to make? You can also see the API staining, which enables them to count and see the bacterial colonies. And here you can see the surface structure of the Mars regolith simulants. They were able to observe that the bacteria either cultivated swimmingly separately or clustering together on particles of the MGS1 as if available, which can also indicate some kind of symbiosis, some kind of working together of those two strands, but it's not looked at in further depth in the scientific paper. Now to the discussion. Both strains showed desiccation tolerance under anoxic conditions. Material in regolith and sugar influence the survivability of both strains after desiccation positively. Both strains are able to withstand desiccation combined with polychromatic UV radiation, which leads us to our conclusion. Butyaxela sp and Salinisphera schabanensis can survive Martian conditions. They did collect sufficient amounts of data. I would say that it was an adequate organism preparation for the Maxim mission, and they were thoroughly tried in the Martian conditions. And I would say that Butyaxela sp and Salinisphera schabanensis are suitable candidates for the Maxim mission, which will hopefully start in 2025. I thank you for your attention. I hope that you learned something new and interesting, and I gladly answer any questions down in the comment section below. Feel free to give your feedback and criticize any points you didn't like. And in the meantime, I hope that you have a nice day.